Coming back to this formula, in practice, you will see that the unit, let's talk about the unit. The unit of C is meter over second. Unit of lambda should be meter, although for visible light, you will see that it's normally in nanometer, which is 1 nanometer is 10 power to the minus 9th meter. So first you have to convert nanometer to meter. And then this one is meter over second, and the H, the Planck constant, is joule second. So the energy itself will have the unit of joule. The energy of the photon will be in joule. Now, sometimes you are asked to solve or to calculate the energy in joule over mole. Now, we haven't yet discussed so much about the mole concept, but at this point, you have to just remember that 1 mole of photons, or 1 mole of anything for that matter, 1 mole of photons is equal to 602 times 10 power to the 23rd photons. So 1 mole of photons is this many photons, and this energy that you get is energy per photon. Therefore, if you are asked to calculate the energy in joule over mole, so per mole, meaning that you are trying now to find the energy for this many photons, so you have to multiply the energy that you get from the Hc over lambda. You have to multiply this with this what we call the Avogadro numbers, but we're going to talk about this more in the next segments. Then from here you will get the energy in joule over mole, and this is the number of photons over mole. That's how you get energy in joule over mole instead of just in joule, which basically is actually joule per photon. This is energy for each photon. If you want to find the energy in 1 mole, then you have to multiply it with the let me write it down for you to remember later. This is what we call the Avogadro's number. We will see more of this in the segments for the mole concept later in the lecture. Now, looking back at the Bohr's model of atomic structure, so in the middle, inside, in the core, you have nucleus made up by positively charged protons and neutral neutrons, and outside you have electron orbiting the nucleus in such a manner in a quantized energy in each of the area that we call the orbitals. The orbits, we would later see that this is called the orbitals that represent a certain energy level, which is why they wouldn't collapse into the nucleus. Now, in this case, we can see that, for instance, we have electron right here, we have electron over there. The electron in the inner part will be closer to the nucleus. Therefore, the electron here is actually more stable and therefore has lower energy. So here inside, you have a lower energy level, and outside here you have a higher energy level. And if we take this into lines, for instance, like this, you have 3 different energy level. Here you have the lowest energy level possible, which is close to the nucleus, that we called as the ground state for the electron right here. Ground state. If you have an electron, normally we represent them with half an arrow like this. The electron here, it can actually move up and then down again throughout the energy levels. So for this electron to be able to move up to this level, then it has to absorb light. when this electron absorbs light, the particle will have enough energy to jump over here. Then we can delete this and move the electron up here. This is what we call as the excited state. The energy that the electron needs to absorb is of course equal to hc over lambda. So the wavelength of the light will be determined through this. This is the energy that is required for the electron that was once here to jump up into the excited state. Now, on the contrary, if this electron is to go back to the ground state, it will emit light. Excited state is normally not the most stable condition for the electron, so the electron will jump back to the ground state, which is a more stable state right here. And during the movement of the electrons from the excited state to the ground state, it will emit light. Again, the light that is emitted, the energy will correlate to this formula. E equals to hc over lambda. So for each energy state, you can determine the energy and the lambda that corresponds to it. Now, say if the electron is trying to jump from the ground state up here to the second level of excited state. If you have this as the first energy and this second energy, of course, now for this electron now to jump up in the blue track right here, so from the ground state to the second level of excited state, then the energy required would be the total of, or the sum of E1 plus E2, where it will also be like this, because don't forget that E is hc over lambda for E1 and also for E2. So when the electron goes from ground state to excited state, so from the inner part to the outer part, it needs to absorb light as the form of energy required, the energy of photons. And while it goes back from the excited state to a ground state, then it will emit light. The energy of the light that is relevant for each of the process will correspond with the wavelength that fulfill this relationship, this mathematical correlation of E equals to hc over lambda. The fact that the electrons needs a certain energy to jump up and down the level, so certain energy level, has also been proven experimentally from the experiments for atomic spectrum. So atomic spectrum is defined as the particular pattern of wavelengths that are absorbed or emitted by any element. And based on the experiment using light with a certain wavelength to be absorbed or emitted by any elements, they found that for any excited atoms of any particular element, they will only emit or absorb a specific frequencies. So they only emit or they only absorbs a specific frequencies. Or on the other hand, we can also say that the frequencies are well separated. So for instance, this is the emission pattern. It will be like line like that. They are discretely separated. So instead of sort of like spectra like that, what they found is that the emission pattern, the emission spectra for any element, they are discrete like this. They only emit at specific frequencies. And this behavior correlates due to the different energy levels, and if the electron wants to move from energy level to other energy level, they need to absorb or emit a certain wavelength, which corresponds to E equals to hc over lambda. So because this is discrete, experimentally by looking at the emission spectrum, where it is a discrete spectrum like this instead of a continuous one. Although the Bohr's model has been accepted and has introduced several important concepts, this model also has a limitation, that it fails to explain the phenomenon at a more complex level for atoms with multiple electrons. So the Bohr's model is mainly useful and accurate for atoms only with one electron. And obviously, in nature, most of the examples of atoms, they have multiple electrons. The next approach to encounter this limitation of the Bohr's model is through the introduction of the quantum mechanics. Quantum mechanics. In quantum mechanics, electron is also, just like light, is also both particle and wave. As wave, each electron, it is defined by so-called wave function or psi. Now taking the psi and square this parameter, the square of the wave function will tell us the probability of finding an electron in a given area or given space within an atom. Okay, now the area where it is possible for us to find an electron is called the orbital. In the next segment, we will discuss about the type of the orbitals and the identity of electrons that is represented in 4 quantum numbers.